Okay, we're working on a 2000 Lexus RX 300 with a 3-liter engine. I believe it's a 1MZ engine code. It's a no start. It was towed in. We brought the car in the classroom. One of the first things we did, of course, is crank it, see if it starts. I want you guys to pay attention to the way this engine cranks. That would be number one. Just listen to it. Go ahead and crank it. Okay, so clearly, when you've done this enough anyway, when you hear an engine that cranks that way, it has a compression problem. You can hear it, it cranks really fast, and one of the first things that you would think of is maybe a broken timing belt. I've seen hundreds of these, and that's what they sound like. Low compression is the direction that we're going so far. It sounds like it has low compression. Let's go to a compression gauge, and we'll pull one spark plug out, take a look at it. We've actually already done that. I'm going to move the camera over to the compression gauge, and let's take a look at that. Okay, so we have the compression gauge connected. We're in the middle cylinder in the front, and go ahead and crank it. Let's take a look at our compression. Keep cranking, keep cranking. Okay, good. All right, so that's confirmed by the way it sounds. It sounds like it has a compression problem. It does, in fact, have a compression problem. You see we have 50 pounds of compression on this cylinder. We did do some other cylinders. I'm not going to take the time in this video to show all of them. The 4 cylinders that we tested, the 3 in the front, the 1 in the back that we can get to, they all had about 50 pounds of compression. Okay, our next process that we chose to do for this vehicle is cam and crank relationship. We have a scope, so we have the ability of comparing the two and seeing whether or not we have a jump timing belt or jump timing chain. I realize on some engines it's very easy to remove the inspection cover and to take a look at those marks, but it's important to know how to do this procedure on a vehicle that you can't do that, especially on an engine with a chain that is not easily accessible. Ways of identifying a jumped timing belt or chain. We're going to do cam crank relationship. So I pulled up the wiring diagram, and on this car we have actually 3. We have 1 crank sensor and there's 2 cam sensors. This being a variable valve timing engine, the VVT sensor is actually a cam sensor, 1 for each bank. And so if you look at this right away, some fundamentals here. 2-wire crankshaft revolution type sensors are generally going to be AC sine waves. They're permanent magnet pulse generators, also known as variable reluctance sensors. So these are going to produce an AC sine wave is what we're looking for. If we scroll down here and take a look at these, one of the things that you want to be able to do right away is you want to be able to recognize some things on the diagram. So first of all, these dotted lines that go around here are shielded circuits. That's a shield, and what that does is that is going to take any electromagnetic interference or radio frequency interference, and it's going to ground those out. So one of the ways you can determine signal wires is by ones that have a shield on it. So these are unfortunately both circled, so we don't know which one the signal wire is on these yet. Let me zoom out one. I want to point something out to you right here, and that is this wire, and this wire. Those 3 are all shared on these sensors. So what we know by that sharing of wires, that's the sensor ground. The sensor signal wires are going to be the ones by themselves. So a very fast way to identify the signal wires, and we can tap into all 3 of these sensors. On this particular car, it's a little bit difficult to get to, so we're not going to do it at the sensor. We actually did it at the computer, and it's going to be these 3 wires. These are my signal wires, and if we follow those, what we actually did is we got a computer pin layout. We adapted to the wires at the computer itself, here and then here. So we got all 3 of these at the computer. I'm not going to show that process. We can do cam and crank signals another time in another video showing instructional how to do that. But in this case, let me show you the picture of what we got. So this is our waveform. This is our crank signal. And these are my 2 VVT signals or my 2 cam signals. Now, unless you have a known good waveform to go by, this is really kind of useless information as far as figuring out whether or not your timing belt is jumped. I want to plug a resource I use. IATN, International Automotive Technician Network, has a waveform library that you can access. Look up the year, look up the make and model and the engine, and guys like me will upload information to help other technicians out. And it is a great resource. We actually did a search on IATN. Unfortunately, on this particular vehicle, we couldn't find a known good waveform, a known good relationship. And so what it ended up doing is making this test really not very useful. So there's some other techniques that you can use to identify whether or not you have a jump belt or chain, and I want to show you another one of those here in a minute. All right, this next step that we chose to do, and this is something that's pretty new to me still, and I'm still learning how to do this more effectively, but it's an in-cylinder pressure transducer test. And what this is going to do is we're taking an electronic signal, so we're actually using a compression test, but we're using an electronic converter. It's going to take that pressure, it's going to convert it to an electrical signal, and we can actually plot our compression on the screen. So that's what we're looking at right here. If you take a look at this one, this is the cylinder that we're connected to, and that would be a representation of near top dead center, or the peak of this would be the peak compression or top dead center in that cylinder. And this would be the same cylinder again right here. And there's a lot of theory that we can do with this waveform. You can plug in valve openings and closings. This is actually 720 degrees of crank rotation from end to end. Actually, the exhaust valve opens around here, intake valve opens here, compression stroke starts around here. Lots of cool information we can put in this. Our main concern though for this wasn't so much that, but we wanted to figure out where the spark was occurring in relation to the height of this compression peak. And so what we did is we brought in another channel, and because this is a coil over plug engine, what we chose to use is the coil primary current ramp pattern. So that's what this red trace is a current ramp. They turn on and turn off of the ignition coil. I know it doesn't look like a ramp, but you need to understand how zoomed out we are. If I were to focus on this red trace for a second and blow that up, you will see that this is in fact a ramp. And it is a normal looking current ramp. So that's not the debate here is, well, one of you, someone may look at this and say, well, that doesn't look like a current ramp pattern, that looks like a square wave. Trust me, it's a ramp, we're just zoomed out. Okay, so a little theory here with the current ramp would be that when the coil is turned on is when it starts to saturate, it's where we build this magnetic field. And when the coil turns off is where our spark occurs. This is when our primary current stops, it's where secondary begins. And so if you look at the waveform, that would be right here is where our coil is going to fire. Put that right in line with the peak of that compression, and what we know by looking at this waveform is that our timing, ignition timing anyway, is right where it needs to be. Okay, so this gives us a little bit of direction as far as we're looking for a jumped timing belt, a jump timing chain. This is a procedure that you can use on any car. In-cylinder pressure transducer, line it up with your ignition firing event, see where it occurs. Truthfully, what we expected to see when we did this waveform is we expected to see this red trace maybe way over here, and nowhere near the peak of this compression waveform, which would have confirmed that we indeed have an ignition timing issue, and then we could proceed and take the covers off and do the inspection as far as the belt or chain goes. But this is the kind of test that will give you some direction. Unfortunately for us, this didn't give us what we wanted, right? Our cam-crank relationship waveform, we couldn't find a known good for that, and then this one is showing us that everything's good, and so we needed to rethink what we were doing. And this is where studying this in-cylinder pressure transducer testing helps. And I'll just give you a little bit of insight. Again, I'm new at the in-cylinder stuff, so bear with me here. But in this waveform, what you're looking at would be compression, okay? And understand too, in this waveform, that there's no combustion taking place because we've removed the spark plug and we have a pressure transducer in its place. So there's no combustion taking place. This first line right here, this dip, is actually cylinders dropping, the piston's dropping in the cylinder. The valves are closed. And the reason that we're going into a negative pressure, this is your zero line right here. If you look right here, 0 psi. We're going into a negative pressure because the valves are closed. They call, there's terms used here, it's called an expansion pocket. I don't want to focus on that one right now. There's some theory in why that pulls low and how it pulls low and into a vacuum. And picture the valves closed, piston is pulling down, creating a vacuum in that cylinder. Again, there's no combustion taking place. Right where this line starts to increase would be where the exhaust valve opens. And so during this period where we're reading basically atmospheric pressure in here, your exhaust valve is open. The next thing that happens is the intake valve would open, and that's what this dip is right here. And so basically from here to roughly here is our intake stroke. Okay? This engine's cranking, and one of the things that we noticed with that little bit of theory, one of the things we noticed is this number was very high. And I'm going to compare these two here. Here's 0 psi, and here is cranking, sorry, this is the exhaust stroke, this is 0 psi, this is my intake stroke, which is showing me a -7 psi. Roughly, pressure to inches of mercury conversion is 1 psi is roughly 2 inches of mercury. So that means that cranking this engine over, we got 14 inches of mercury cranking this engine over. I have never seen an engine with this high of cranking vacuum, ever. 14 inches. That's crazy. So this is where we're at. Thinking about this process, I'm going to show you where we went next. Okay, what I want to show is what a conventional vacuum gauge looks like on this engine, and we'll try to compare this to our pressure transducer testing. I realize that most of you out there don't do pressure transducer testing, so I don't want to scare you by that test. I really wanted to show that because we truthfully thought that that in-cylinder pressure test compared to ignition timing was going to show us what we wanted to see. It didn't. And so we saw a very, very low intake vacuum pocket when that valve opened. And now again, when you're looking at it on a scope, you're looking at certain time frames. And actually what we found is the vacuum's even going deeper than what that capture showed me that I showed you guys on the screen. So go ahead and crank it and let's watch this intake. Oh wait, before you do that, the line that we want to look at is this line right here, this 0, 5, 10, 15, 20. That is your vacuum line. Let's take a look at what our intake vacuum looks like on a crank. Go ahead and crank it. Keep cranking. Keep cranking. All right. So you see we had like 22 inches of vacuum on a crank. I mean, that's insane. I've never seen anything like that before. For our vacuum to be that high during a cranking condition, and you saw how it bled off real slow, it means we have an intake restriction. And let's compare this real quick to the compression gauge again. Can you hold that gauge? Let me zoom out just a little bit. Hold that gauge, yeah, turn that around right there. And vent that pressure out. Angle the gauge up right there. A little bit more, right there. Yep, getting the light right there, good. Okay, can you crank that again, please? Okay, good. So you saw we're still only getting 50, 55 pounds of pressure compression, and our vacuum is extremely high. And so again, what we're looking for is an intake restriction. We pulled the air cleaner, we took a look, there was no squirrel nest in the air intake. And honestly guys, what we found, and this is crazy, but this idle air control motor is stuck shut. The throttle body's just a little bit dirty, so it's restricting the throttle plate. Typical maintenance item that needs to be done. Main problem with this vehicle is a stuck shut idle air control valve. In most cases, and this is where we can become complacent because we do so many of these compression tests on fuel-injected cars. And what we find is that we don't need to open the throttle to get a different reading. I know when we're taught compression testing, we open the throttle up. But because of the way fuel-injected cars are designed, with the idle air control passage being fully open during a cranking situation, we have found that opening the throttle really doesn't make much difference at all on a fuel-injected car. And so we get a little lazy and not do it the way we're supposed to. Guys, when we open the throttle up on this car, this engine actually runs. We can maybe show you the compression pressures, but I think more importantly would be to open the throttle up a little bit for me, Jordan, and crank this thing over. Shut it off. Let's get this spark plug put back in this one hole, and then we'll see what this thing looks like. We'll do a clear flood crank, or we'll disable the spark, get a compression reading with this throttle open, just to show you a comparison. But you can see that this engine runs. Engines with 50 pounds of compression don't run. The reason this thing had 50 pounds of compression, it's not breathing. It's not pulling air in, so it's not compressing it. And we have an air intake restriction. I've never seen this before to this level where it affected compression like that. This was not a mechanical problem. This is an idle air control problem. So again, we're going to put this plug back in, do one more measurement. Just a warning to you guys out there, might want to open the throttle when you do compression tests. All right, what we've done is we've taken the EFI main relay out. There is no clear flood on this car. So to keep the car from starting, we're going to hold the pedal to the floor at wide open throttle, just because when you do a compression test, that's typically what you should be doing. Go ahead, hold the pedal to the floor and give me a crank. Okay, good. So you saw our cranking vacuum was basically 0, which is typically what you would find 9.9 times out of 10 when you do a cranking compression test, even on a fuel-injected car. You don't need the throttle open to change your reading. This one's been unique here. What's our compression pressure on that gauge showing? Mike?
Almost 150.
150 pounds of compression as opposed to 50 just by opening the throttle. So the variable here, of course, again, make sure you open the throttle when you're doing compression testing. Don't jump the gun on this. When you see that kind of cranking vacuum, you have an air intake restriction. That's what we had. And in fact, here's what else we can do with where we're at. You can let those go. I'm just going to talk for a second. What else we can take from this, guys, is we can take our cam crank relationship picture that we didn't know was good or bad. In fact, because this car runs, we could probably call that picture a known good. So future reference, we ever get another RX 300 in, we have a known good cam crank relationship picture now. Certainly that in-cylinder pressure transducer was key, but again, you could have found this just by a cranking vacuum test, and I gotta be honest with you, I don't use cranking vacuum very often because most fuel-injected cars, like I said, you don't have any cranking vacuum, so it's not a very valuable tool in most circumstances. But you see here, cranking vacuum was critical. I mean, 22 inches of cranking vacuum, you didn't need a scope to identify that one. That's where we were. So I want to end this video here. Part 2 of this, I want to shoot it, is how to check the idle air control motor, how to check the wiring. This is a rotary type, it's got 3 wires. So part 2 of this, we're going to address this vehicle as it came in as a car that runs as long as your foot is on the gas pedal, but does not run when you let your foot off the gas pedal. And that's exactly what's happening with this car. Jordan, go ahead and start it so we can hear that. Hold your foot on the pedal a little bit. Oh, hold on. It's not going to start with this EFI relay out, is it? You guys want to throw that plug back in? We'll take a listen to what this sounds like with all the cylinders hitting too. All right, so we got the plug back in, got the main relay back in. I'm going to hold the throttle open out here. Go ahead and start the car. Here, this is a pretty smooth running engine as long as my foot's on the not my foot, sorry, my hand is on the throttle. I'll let go of the throttle. Second you let go of the throttle, the car stalls. One of the symptoms of an idle air control issue is exactly that, a vehicle that runs fine as long as your foot is on the throttle, but stalls when you let your foot off the throttle. Immediately our focus is going to go toward an idle air control problem. So let's back up for a second. This car comes in the shop and sounds like it sounded with the cranking compression the way it was. We may not have thought to open the throttle, but had we have done that, simply opened the throttle to start this process, we would have never went down the path we went down. So just a little word of caution, definitely a good one to show you guys. Part 2, we're going to check out this idle air control. Okay, the last thing that I want to do for you guys is provide bad information. And in that last capture, I was showing the same relationship. What we found out after finishing this car is our 2 T-pins for these 2 VVT sensors were actually contacting one of the VVTs, and that's why they were lined up. So if you guys in the future are going to use this waveform as a known good, this one is now, we can confidently call this a known good. I didn't want you using that last picture, so I added this to here. I can zoom in just a little bit more for you guys if you want a little bit of detail. And what you can do with this is you can say, follow your sync knots for your crank, which is right here. Kind of get an idea where this one VVT signal is, and then I'll put you right in the middle of this other VVT signal. Count these: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just over 10 teeth past the sync knots for the second VVT. I just don't want you guys using bad information, and that last capture was bad information.